In this view, we're going to see an entire example, start to finish, of using the Laplace transform to solve a differential equation. This differential equation, x double prime plus x equal to f of t, has the special feature that f of t is a piecewise defined function. This could cause a lot of problems for us if we were using other methods, but with the Laplace transform, we're going to be able to deal with this kind of piecewise defined function relatively nicely. It also comes with two initial conditions that x of 0 and x prime of 0 are both 0. Okay, so I want to take the Laplace transform on both sides. First, let me use the terminology that the Laplace transform of x of t is going to be equal to capital X of s, and so I'll use that as a shorthand. I'm going to take the Laplace transform of both sides, so the first thing that's going to get hit is the x double prime. And when you take the Laplace transform of that, well, two derivatives, as we've seen in the past, gives you an s squared, and then multiplied by the x of s. Normally, there would be then minus an s times an x0, and then minus an x prime of 0, but since both of those initial conditions are 0, I don't have any of the other terms. Then I have a plus x, which is going to become under the Laplace transform the capital X of s. And then on the right-hand side is the Laplace transform of whatever f of t is going to be. I could then perhaps clean this up a little bit and say that capital X of s is going to be, well, the Laplace transform of f of t, whatever that is, and then divided out by s squared plus 1. Okay, so now we turn our attention to what is the Laplace transform of this f of t. Because it's piecewise defined, it's going to be convenient to write this in terms of step functions because, as we've seen in the previous video, we understand how to take the Laplace transform of a step function multiplied by some other function. Okay, so let's try that. That is, I want to take this f of t and rewrite it from its original definition now in terms of step functions. I see that it starts and it's 0 in the region 0 up to 1, so it doesn't do anything there, but then it gets turned on in effect at the value of t equal to 1. So the first thing I'm going to do is write the step function u of t minus 1, and what the effect of u of t minus 1 is it's 0 to the left of 1, and then it's just 1 to the right of 1. And what does it get multiplied to? In this next region, it gets multiplied by a t minus 1. And that's great, except I also have this third portion of the piecewise defined thing. So I in some sense need to turn off the t minus 1 function and replace it with just the function 1. The way that I'm going to do this is I'm going to subtract off a step function t minus 2. So this is a step function that does not contribute anything until t is equal to 2, and then it starts having the value of 1. And because in the region t greater than 2, I want the net result to be 1, since I already have a t minus 1 from the first term, I'm going to multiply this by a t minus 2 in the second term, and then t minus 1 minus t minus 2 is just going to give you the value of 1. So indeed, if you plug in a number here like t equal to, I don't know, say 7, the first term is going to give you 6, the second term is going to give you 5, and the difference between those is going to give you 1, exactly what it's supposed to be for values of t that are greater than 2. So making a bit more room, now our goal is the Laplace transform of f of t. And I want to remind you of a nice fact before we try to do this, namely that we had studied in our previous video how to deal with expressions like this, Laplace transform of u of t minus a times some function at t minus a. And what this was going to equal to was e to the minus at multiplied by the Laplace transform just of the function f of t itself, not shifted now by t minus a. So then if I look at what my function f is, I see that in both cases I have these step functions, one at t minus 1 and one at t minus 2, and then they both multiply to some particular function. That is, they both look of this formula. That is, they both look a lot like the form needed for this particular formula. So what does that give me? Well, the first one, e to the t minus 1, so that's an a equal to 1, gives you an e to the minus t on the top. And then I have to think, the function is f of t equal to t. I know it says t minus 1 there, but the t minus 1 part is the shift. The underlying function itself is just f of t equal to t. And the Laplace transform of the function t is, well, 1 over s squared. So this is e to the minus t divided by s squared. Very similarly for the second one, now it's an e to the minus 2t because it's a different value of a, t minus 2 now. And then it multiplies by this t minus 2, which again we think of as just the function t, but shifted by this value of t minus a, where a is equal to 2. So again, it's the same function, and so again, its Laplace transform of t is just 1 over s squared. So that's the Laplace transform of this expression. Okay, so putting it back to the beginning, then what I have is that this big X of s is, well, an e to the minus t over s squared plus 1, and then minus an e to the minus 2t over s squared plus 1 once again. So I'm almost done, except for the fact that I have to still do the inverse Laplace transform. I've taken the differential equation, I've converted by the Laplace transform to this new algebraic equation, and I've solved that algebraic equation, and I've noted that pleasantly, the piecewise defined nature of the f of t is sort of gone away. I've got this sort of nice continuous function down here in Laplace world, if you want to call it that. So when I go away, leaving Laplace world back to the differential equation world, I have to undo this process. So how can I do this? Well, the e to the minus t and the e to the minus 2t parts, I'm not so worried about. Those are going to be very similar to just what I did. They're going to introduce a step function and denote some sort of shift. Those are going to be dealt with just basically exactly what we just did. So now what I want to focus on is these denominators here, and I really want to just investigate the 1 over s squared times s squared plus 1 portion. I'm going to first do a little bit of algebra. I can do partial fractions on this. We've seen in previous videos, and I'll do it very quickly here. The 1 over s squared is a repeated linear factor, and so I write it as a divided by s plus b divided by s squared. I then have an irreducible quadratic in the s squared plus 1, and so this is going to be a cs plus d divided out by s squared plus 1. Now the goal is to solve for the a, b, c, and d. We've seen several of these examples before, so I'm not going to do it. I'm just going to assert for you that in this specific case, it is a equal to 0, it is b is equal to 1, then it's a c equal to 0, and a d equal to minus 1 divided by s squared plus 1. I'm asserting that's the answer, but please feel free to pause and verify that that's true. And the point about this is that now I can compute a little bit more easily the inverse Laplace transform of 1 over s squared minus 1 over s squared plus 1. Well, 1 over s squared is the type of expression you get for a polynomial. Indeed, it's the Laplace transform just of t, so I will assert that. And then 1 over s squared plus 1 is also one that we should recognize from our past. This is sine of t. So it's t minus sine of t is this answer. All right, so I'm going to go back up a little bit here and remind us that this big X of s is the thing that we're trying to take the inverse Laplace transform of. We've sort of gone and dealt with it if there was no exponentials. I just looked at the 1 over s squared times s squared plus 1 factor and figured out how to deal with that. But now I'm going to go back to the original. And so the way the original is going to work is I have to deal with these negative exponentials. The effect of the negative exponential is, I could probably still have it if I scroll up here, is what is happening in the red. The effect thus of the negative exponential is to do precisely what we've seen previously. You just multiply by this step function and shift it value by the value of a. So if I go back down to where I'm trying to do my work here, so thus for the first term, I'm going to get a u of t minus 1, and that's going to multiply, well, this thing that I've already computed, but now at the value of t minus 1, that's the contribution of the negative exponential. So it is, instead of a t, I write a t minus 1, and then instead of a sine of t, I write a sine of t minus 1. That's just dealing with the first term. Then I'm going to have a negative. It's now an e to the minus 2t, and so it is the step function u of t minus 2. And then we do the same trick. It's going to be the same inverse Laplace transform, but shifted in the same way. So instead of a t, it's going to be a t minus 2. And then I'm going to have a subtraction of a sine of t minus 2 as well. So this here is all little x of t, and that is my final answer. So we've seen once again a full example in this process where we go from a differential equation, we take the Laplace transform, we have to do sort of algebraic trickery away in Laplace transform world. We get some result and we do an inverse to get back to the original solution to the initial value problem. So I hope you enjoyed that video. If you did, give it a like. There is many more videos in the Laplace transform series. Check out the links in the description for the playlist on that. And we'll do some more math in the next video.